Okay, so we ended with chapter 4, and now we're going to start with chapter 5. So chapter 5 is gases. Okay, so the first question that you might ask is, how do you measure gases? How do you measure the presence of gases? Well, one way that we can measure how much gas we have is we can look at pressure. There's several units of pressure that chemists commonly use, so we can discuss pressure units that we're going to use to measure our gases with. So the common unit that we use for pressure is atmospheres. So here is 1 atmosphere. This is what you have at atmospheric pressure. And 1 atmosphere is equal to 760 millimeters of mercury, and this also is equal to 760 torr, where torr is short for torricelli. Okay, so this is actually the common units of pressure that chemists use. So for the purposes of this chapter, this is basically what we're going to be using for pressure for everything. This is not the only units of pressure that one can run into, so we also have PSI. So 1 atmosphere is equal to 14.7 PSI, where PSI stands for pounds per square inch. So PSI is what people use for measuring pressures and tires and things like that. These are units that engineers and people like that tend to use. Chemists mostly, as far as this chapter goes, this is what we're going to use: atmospheres, millimeters of mercury, and torr. But in addition to PSI, engineering types also sometimes look at pascals. So 101.325 pascals is another commonly found unit of pressure. So for the purpose of this chapter, I would recommend memorizing this, but probably on the next exam, I will give you some equation like this somewhere at the top of the exam, right under your name. So if you don't have it memorized, if you recognize that this is the units of pressure that we're dealing with, you can probably get by. Okay, so then we're going to measure pressure, but we're also going to look at other things related to measuring how much gas you have, and those would be things like volume, temperature, pressure, and number of moles. Now we're going to look at some simple gas laws. And a lot of these are sort of very intuitively reasonable. What you'll find is that these simple gas laws relate pressure to volume, to temperature, and the amount of gas you have, or the number of moles. We're going to use the common units for all of these. So we're going to say common symbols for all of these, and also the same units. So one of the things that we find in our simple gas laws is V for volume. And really, even if you don't have memorized that V is equal to volume, it's kind of obvious. V, the very first letter of the word volume, is the symbol for volume. And these are usually given in units of liter. For the purposes of solving gas laws, they are almost always exclusively in units of liters. Then we have T, which represents temperature. And once again, even if you don't know that T represents temperature, I mean, it's intuitively kind of obvious. So the unit of temperature is Kelvin, or capital K. And then we have pressure. So P for pressure. Pressure is, for the purposes of the gas laws, are always given in atmospheres. And then we have N for number of moles. We've actually been using N for number of moles in other equations before we got to this chapter, so here it is back again. So we're going to relate these variables to each other in our simple gas laws. So here are our simple gas laws. After we go over the simple gas laws, I'm not going to so much hold you responsible for being able to deal with the simple gas laws, but after we go over the simple gas laws, we're going to combine all the gas laws into the ideal gas law and the combined gas law, and we're going to be able to use those two gas laws to represent all of the variations of the simple gas laws. But here are the simple gas laws. So our first simple gas law is Boyle's law. So what we have in Boyle's law is that volume is directly proportional to the inverse of pressure. And this is at constant temperature and number of moles. Another way that I can write this equation is also if I set two different pressures and two different volumes, I can come up with this equation. P1 times V1 is equal to P2 times V2. And this is really a very intuitively kind of obvious sort of idea where if you have a balloon and you squeeze the balloon, you would be increasing pressure, and then your balloon would get smaller. Squeeze. You would increase pressure and your volume would become smaller. So it's that kind of intuitive idea that if you squeeze a balloon, the balloon gets smaller, but you're also increasing the pressure within the balloon by squeezing it. So it's a very intuitively obvious kind of thing. So here are my two ways that I can write Boyle's law. This is how you would normally use the equation. All right, so here's our next simple gas law. This is our Charles's law. And Charles's law is at constant pressure and number of moles. So these are both for the same amounts. So this is for the same amount of gas, different pressures and different volumes. So here, our Charles's law says that volume is directly proportional to temperature. Or if I have two different gases, I could write it as volume 1 over temperature 1 is equal to volume 2 over temperature 2. Or if you think about that same balloon again, that where you haven't added any gases to it, that you have the same balloon. If you heat the balloon, the volume would increase. So intuitively a very reasonable sort of thing once again. And here is our normal writing of the Charles's law for most purposes. So these are the equations that you would use if you were doing a word problem with Boyle's law or a word problem with Charles's law. Now we can also represent this, we have one more simple gas law. So these are all my simple gas laws. So here's one more simple gas law, and that is our Avogadro's law. So for Avogadro's law, which is at constant temperature and pressure, Avogadro's law says that volume is directly proportional to N. That little sideways looking thing there, this little symbol represents is proportional to. So Avogadro's law says that volume is directly proportional to the amount of gas you've got, or the number of moles. And if you sort of think about what this would look like in terms of our balloon, this would be where you add more gas to your balloon by blowing into the balloon. So for our little equation, we would say volume 1 over N1 is equal to volume 2 over N2. So here is a representation of Avogadro's law. So now we have the simple gas law. So you've got Boyle's law, Charles's law, and Avogadro's law. So now what we're going to do is we're going to combine all of the simple gas laws to give us a combined gas law that represents everything, which we will call the combined gas law. And then we're also going to have something called the ideal gas law. So the ideal gas law also does have all of our components of the simple gas laws all sort of combined together. So here, let's take a look at first the ideal gas law. Ideal gas law is only obeyed by ideal gases. They're not obeyed by non-ideal gases. But usually, the only things that are non-ideal gases are if you have a gas at very, very high pressure or very, very low temperature. That's the only case when you would have non-ideal gases. Almost all the rest of the time you have an ideal. So here's our ideal gas law equation. PV is equal to nRT. Now the symbols are the same as they were in our simple gas law. So P represents pressure, V represents volume, N represents the number of moles, and T represents the number, the temperature of our gas. Now what's our R? R is the ideal gas law constant. So R is equal to 0.08206 liter atmosphere per mole Kelvin. So here is our ideal gas law. The only thing you have to watch out for when you're trying to solve a word problem involving the ideal gas law is you just have to keep your units consistent, and you have to make sure to have the correct variable represent the correct thing, and then there's really no other way that you can mess up this problem involving the ideal gas law, because other than, as long as you have that straight, this is like the easiest chapter in the entire book. Now, when we're dealing with our ideal gas law, we have to keep our pressure in atmospheres, volume in liters, temperature in Kelvin. So as long as we have the correct units and we have our ideal gas law, we're good to go. I would recommend maybe memorizing the ideal gas law and the gas law constant. I had to memorize it when I was a college student. But probably on the next exam, the ideal gas law and the gas law constant will probably appear right under your name. And as long as you recognize that you're going to actually have to use the ideal gas law, you should be fine. Okay, now the other thing that we get out of the ideal gas law is if you actually take one ideal gas law and divide it by another ideal gas law. So if you have for the same amount of gas, so for N is equal to the same number. If I had two different conditions, so if I have P1, V1 is equal to NR, T1, and then I had the same gas at different conditions, same amount of gas at different conditions, where I have P2 times Z2 is to NR, T2. I now have two ideal gas laws for the same amount of gas. So for the purposes of our ideal gas law equation, these two numbers would be identical because you're dealing with the same number of moles of gas, and the ideal gas law constant obviously doesn't change. So I can actually divide one entire equation by the other entire equation, and then I end up with P1 V1 over P2 V2 is equal to NR T1 over NR T2. And because we said we have the same number of moles, because we're not dealing with a different amount of gas or a different identity of gas, it's the same gas at different pressure temperature conditions, those two things would cancel out. The NR would cancel out. And then our ideal gas law equation would become this. So this is known as the combined gas law. Now, if you look in your textbook, they arranged it a little bit differently, but it's basically the same equation. They just arranged it a little bit differently so that the actual variables don't show up exactly in the same place. But here are the two equations that we're going to be using during the course of this chapter the most. So here is our ideal gas law, and here is our combined gas law. Now, for both the combined gas law and the ideal gas law, it's probably best to keep the pressure, atmosphere, volume, liter, temperature, and Kelvin, so that you don't have any funny things going on when you try to substitute something with the wrong units. If you're not very careful, you will end up with the wrong answer. So what's nice about using this is the combined gas law really combines all the simple gas laws. So it combines Boyle's law, Charles's law, Avogadro's law. Well, it doesn't combine Avogadro's law, but it combines Boyle's law and Charles's law. So for instance, if you have the same temperature, then temperature 1 is equal to temperature 2, so you'd end up with T1 over T1. This becomes 1, then this equation becomes Boyle's law equation. If you keep the pressure constant, so if pressure 1 is equal to pressure 2, this would cancel out, and then you'd have volume 1 over volume 2 is equal to T1 over T2, which is just Charles's law rearranged. So this would give you Charles's law. So the combined gas law really does combine all the gas laws. So I would suggest instead of memorizing Boyle's law and Charles's law separately, that you just know combined gas law. And then if you use the combined gas law, it really has in there Charles's law and Boyle's law all together, all combined together into one nice equation. Once again, I will provide the combined gas law somewhere on the exam. I will not provide you with individual Boyle's law, Charles's law, Avogadro's law separately, but I will provide you with combined gas law. So these are the two equations that you're going to be using in all the word problems that follow. Okay, I'm going to give you some examples in a minute of the word problems, but those are the equations that we're going to use. And really, I think this is one of the easiest chapters as long as you keep your units straight and you don't forget that pressure is represented by P and volume is represented by V and temperature is represented by T. You should be fine.